Mountain View, California, late spring 1970. Inside a cramped, overheated building that used to be a warehouse, a young engineer pulls a silicon wafer out of a test rig and stares at it under the light. Row after row of tiny rectangular dies. Almost every single one has failed. He doesn't say anything. He just sets it down next to the pile of identical wafers from that morning and the morning before that and picks up the next one. Somewhere behind him, an alloy furnace lets out a low groan and blows its cap again, the third time that week. Someone has started a betting pool on how far it'll fly. This was supposed to be the chip that changed computing forever. Instead, it was failing almost every test the company threw at it. Yields were catastrophic. Customers were getting nervous. And a tiny company that had bet its entire existence on this one product was running out of time to make it work. Nobody in that building knew it yet, but within 18 months, this chip, flawed, temperamental, almost cancelled more than once, would become the best-selling semiconductor device on planet Earth. It would end a 50-year reign of a completely different technology. It would sit inside computers built by 14 of the 18 largest manufacturers in the world. And it would lay down the blueprint for every stick of memory inside every phone, laptop, and server built for the next half-century. The chip was called the Intel 1103. And the story of how it went from a company-ending disaster to the foundation of modern computing starts with two men who had already walked away from one company and were about to bet everything on a piece of silicon nobody thought could actually be built. To understand how close this came to never happening, you have to understand what memory meant to a computer in 1968 and what it cost to build. Every calculation a machine ran, every number a program needed to hold on to, even for a fraction of a second, lived somewhere physical, a place with weight, wiring, and a price tag. For 20 years, that place had been magnetic core, and nobody who had ever seen core memory built by hand ever forgot it. Picture a factory floor, rows of women bent over microscopes, each one threading a hair-thin copper wire through a ring of magnetized ferrite smaller than a grain of rice. One ring, one bit. A single kilobyte of memory, the kind of capacity a modern phone burns through loading a single icon, could require thousands of these rings, each one hand-strung into a woven lattice of wires by a human being with steady hands and a lot of patience. It was slow. It was expensive. It was also, for 2 decades, the only thing anyone trusted enough to build a real computer around. Core memory didn't forget things when the power went out. It didn't drift or degrade. It just sat there, magnetized, reliable, and absurdly labor-intensive to produce at any real scale. By the late 1960s, that labor-intensive reliability had become a ceiling. Computers were getting more ambitious. Programs were getting bigger. And every additional kilobyte of memory a computer maker wanted to add meant more rings, more wire, more hours of human hands doing work that no amount of automation had ever fully replaced. If someone could find a way to store that same information on a sliver of silicon instead, something a machine could stamp out by the thousands instead of a person threading wire by hand, the economics of the entire computer industry would change. The question was whether anyone could actually build a chip good enough, cheap enough, and reliable enough to do it. In 1968, Robert Noyce and Gordon Moore left Fairchild Semiconductor, the company that had made them both famous in the tight, paranoid world of Silicon Valley chipmaking. Noyce had co-invented the integrated circuit. Moore had spent his career watching transistor counts double and would soon have his name attached to the most famous prediction in tech history. Between them, they had the kind of reputation that could raise money on a handshake and a napkin sketch. Investor Arthur Rock backed them with barely more than that. They called the new company Intel, short for Integrated Electronics, and from day one they made an unusual bet. Most of the semiconductor industry in the late 1960s was chasing logic chips, the circuits that did the calculating. Noyce and Moore looked at a different target: memory. Every computer on Earth at that point stored its working data in magnetic core memory, a technology that had barely changed since the 1950s. It worked by threading tiny magnetized rings, cores, onto a woven grid of wires, with each ring holding a single bit of information as a magnetic charge. It was reliable. It was also enormous, expensive, painfully slow to manufacture, and it topped out hard as computers demanded more and more memory. Noyce and Moore believed silicon could replace it. If you could put memory directly onto a chip the way you put logic circuits onto a chip, You could make something smaller, faster, and eventually dramatically cheaper than a technology that had to be hand-woven, literally by rows of workers threading wire through rings under microscope. It was a good idea. It was also, in 1968, mostly theoretical. Nobody had proven a semiconductor memory chip could outcompete core memory in the real world, at scale, at a price computer makers would actually pay. Their third employee was a Hungarian immigrant named Andrew Grove, a chemical engineer who had fled Budapest in 1956 during the Soviet crackdown, arrived in America with almost nothing, and built a doctorate and a career out of pure, relentless discipline. Grove didn't have Noyce's charisma or Moore's quiet brilliance. What he had was an obsessive, almost frightening intensity about getting things right, and a total lack of patience for excuses. That combination, Noyce's vision, Moore's technical instinct, and Grove's ferocious execution, would end up mattering more than anyone could have guessed, because Intel's first two products were, to put it plainly, unimpressive. The 3101 was a small, fast memory chip that stored just 64 bits, 64 individual digits of information. The 1101 that followed held 256 bits. Both worked. Neither one set the industry on fire. 2 years in, Intel was still losing money, still unproven, still a small outfit trying to convince an industry that silicon memory was the future rather than an expensive experiment. They needed something bigger, something that would force the rest of the computing world to pay attention. They were about to get it from a company that wasn't even in the chip business. In 1969, an engineer named William Regitz at Honeywell, one of the giants of the mainframe computer industry, had an idea. Along with his colleague Bob Probsting, he had worked out a new kind of memory cell, one that used just 3 transistors and a tiny electrical charge stored in a capacitor to represent a single bit of data. It was called dynamic memory, or DRAM, because unlike the simpler static designs of the day, the charge would slowly leak away and had to be electronically refreshed, read and rewritten thousands of times a second just to keep from forgetting itself. It was an elegant idea on paper. It was also a serious gamble. A 3-transistor dynamic cell meant you could theoretically pack far more memory onto a single chip than anything built before, 1,000 bits instead of a few hundred. But nobody had proven it could actually be manufactured reliably. Regitz didn't have a chip company, he had a concept, and he went looking for someone willing to build it. Intel said yes. It was, by any sober measure, a reckless move for a company that was still in the red. Going from 256 bits to 1024 bits wasn't a modest step up. It was a fourfold leap in complexity, attempted with a fundamentally different, unproven cell design, on manufacturing processes that were themselves barely mature. Andy Grove later admitted, without much romance, that it required taking real technological gambles, and that the pressure on the team was constant enough that the engineers spent almost as much time arguing with each other as they did solving the actual problems in front of them. Memory engineers against process engineers against test engineers, all locked in the same overworked, underfunded building, all racing against a clock that could end the company. The chip got 2 internal names, the 1102 and the 1103, developed side by side under the leadership of an engineer named Joel Karp, working hand in hand with Regitz himself. Ted Hoff conceived the underlying approach. A designer named John Reed turned it into an actual circuit layout. Eventually, only one of the 2 designs, the 1103, would make it to market. The other was quietly abandoned. What nobody in that building fully appreciated yet was how much punishment the manufacturing process itself was about to take. Picture the Intel of 1969 and 1970, not as a gleaming Silicon Valley campus, but as a single overloaded facility in Mountain View, straining under the weight of what it was being asked to do. According to later accounts from people who worked there, the building was in genuinely rough shape. Roof timbers cracked under the load of process equipment that had never been designed to sit where it was sitting. Sump pumps flooded. Ovens meant for chemical processing got repurposed to reheat food for company potlucks, because there wasn't anywhere else to put them. And that alloy furnace, the one responsible for a critical step in making the chip's electrical contacts, kept blowing its cap with enough regularity that employees turned it into a running joke, guessing how far across the room the lid would fly each time it happened. This was the environment in which engineers were trying to perfect a process demanding almost surgical precision. Circuit features just a few millionths of a meter wide, on silicon wafers that had to be kept immaculately clean, built by workers in protective suits trying to keep human skin, hair, and breath away from surfaces that a single stray particle of dust could ruin. And ruin them it did, over and over. When the first 1103 silicon came off the line in 1970, the yields, the percentage of chips on a wafer that actually worked correctly, were dismal. Some accounts put early yields below 10%. That meant that for every 10 chips a wafer produced, 9 was scrap. At those numbers, the economics didn't just look bad, they looked impossible. You cannot sell a product profitably if 9 out of every 10 units you make are garbage, and you especially cannot do it when the company selling it doesn't have deep pockets to absorb the loss while it fixes the problem. Worse, the chips that did pass weren't fully trustworthy either. The 1103 had a quirk that would come to haunt the entire project. Under certain conditions, specific combinations of temperature, timing, and electrical noise, the chip would simply fail to hold onto the data it had just been given. It would forget. For a memory chip, there is no more damning flaw imaginable. The entire point of the device was to remember things reliably. Instead, in edge cases nobody could fully predict, it just didn't. Intel pressed forward anyway, because there was no version of the plan that involved quitting. They revised the manufacturing masks, the stencil-like templates used to etch each layer of the circuit onto the silicon again and again and again. The first version didn't work well enough. Neither did the second, the third, or the fourth. It would take 5 separate mask revisions before the process stabilized enough to manufacture the chip reliably in volume. Each revision meant weeks of retooling, retesting, and re-explaining to increasingly nervous customers why the product they'd been promised still wasn't shipping in the numbers they needed. And then, just as things were fragile enough already, a decision made to solve one problem very nearly created a second, far bigger one. To meet demand and reassure customers who were wary of relying on a single, struggling supplier, Intel had lined up a second-source manufacturer, a Canadian company that would produce the 1103 under license, giving buyers an alternative supply chain in case Intel's own fab couldn't keep up. On paper, it was smart risk management. In practice, it became a crisis of its own. The Canadian manufacturer, trying to boost its own yields, deviated from Intel's exact specifications, shrinking the chip's physical size and shifting to larger wafers to try to squeeze out more dies per batch. It was a reasonable engineering instinct. It was also a mistake. Instead of improving yields, the changes collapsed them, pushing the Canadian line's output toward almost nothing. Now Intel had a partner that was supposed to be sharing the manufacturing burden, and instead was producing next to nothing usable, while draining engineering time and attention the main Mountain View team desperately needed for their own fight. Inside Intel, the strain boiled over into open conflict. Andy Grove, watching resources get pulled in 2 directions at a moment when the company's entire future depended on getting one chip right, argued furiously that Intel could not simultaneously fix its own yield problems, keep its primary fab running, satisfy the customers already waiting on shipments, and prop up a struggling partner 3,000 miles away, not with half the engineering staff effectively split across 2 countries. In the heat of one confrontation, he is remembered as warning, in essentially those terms, that continuing down that path would be the end of the company, not a setback, the end. It's worth sitting with what that moment actually was. This wasn't a Fortune 500 giant weathering a rough quarter. This was a young company, still unprofitable, whose entire identity and survival rode on a single unfinished product that kept failing in the lab and now had a second, tangled failure happening on another continent. If the 1103 didn't work reliably, affordably at scale, there was no backup plan. There was no second product line big enough to save them. There was just the door. Something had to change, and it wasn't going to be luck. What actually pulled the 1103 back from the edge wasn't a single flash of inspiration. It was the same unglamorous weapon that has rescued more engineering projects in history than any stroke of genius: relentless, obsessive measurement. Grove threw himself into the manufacturing process with an intensity that colleagues found almost unsettling. He pushed the fab toward what would later be recognized as an early, disciplined form of statistical process control, tracking every variable in the manufacturing line, not just the finished chip's pass-fail result, but the dozens of upstream factors that determined whether a wafer would succeed or fail long before anyone tested it. Contamination sources were tracked down and eliminated one by one. Cleanroom procedures were tightened. The workers in their protective suits, once a somewhat improvised precaution, became part of an increasingly rigorous discipline about what was and wasn't allowed anywhere near a wafer in process. It was not fast, and it was not clean. It was thousands of small corrections compounding on top of each other. A slightly different etching time here, a tighter contamination tolerance there, a redesigned furnace step to stop the alloy step from behaving unpredictably in the first place. Every failed wafer was information. Every batch that came out slightly better than the last one told the team something about which change had actually mattered and which hadn't. By the time the fifth mask revision was locked in 1971, the picture had genuinely changed. Yields had climbed out of the single digits into workable territory. The mysterious data loss quirk had been engineered around, tamed through tighter timing margins and design refinements that made the chip's behavior far more predictable across real-world operating conditions. The 1103 wasn't just a promising concept anymore. It was something you could actually build, ship, and rely on in volume. And once that threshold was crossed, everything moved fast. There's a particular kind of relief that only shows up after a long enough stretch of failure, not celebration, not yet, just the quiet, almost disbelieving realization that the numbers on the test sheet finally looked the way they were supposed to look months ago. That's roughly what it felt like inside Intel in early 1971. Wafer after wafer came off the line, and instead of 9 dead chips for every survivor, the ratio had flipped. The furnace still misbehaved occasionally. The building was still cramped and overworked. But the product itself, the thing the whole company had been built to prove could exist, finally worked the way it was supposed to, batch after batch, without anyone holding their breath. By the end of 1971, the 1103 had gone from Intel's biggest liability to its biggest asset. Priced at around 1 cent per bit, a small fraction of what an equivalent amount of magnetic core memory cost to build. The chip suddenly made brutal economic sense to computer manufacturers who had spent 2 decades paying a premium for hand-assembled core arrays. The adoption curve was staggering for a technology that had nearly collapsed under its own manufacturing problems a year earlier. Hewlett-Packard put it into their 9800 series computers. Digital Equipment Corporation, one of the most influential computer makers of the era, adopted it for the PDP-11 line, a machine that would go on to shape an entire generation of computer science. Honeywell, the very company whose engineers had dreamed up the underlying cell design in the first place, built it into their own minicomputers. Control Data Corporation came on board. By the close of 1971, the 1103 had become the best-selling semiconductor memory device in the world. Within another year, 14 of the 18 largest mainframe computer manufacturers across the United States, Europe, and Japan were building it into their machines. Intel didn't stop refining it once it started selling. In 1973, the company released the 1103A, an improved version with better timing margins, lower power draw, and compatibility with standard logic circuitry that made it dramatically easier for engineers to design around. It was built to slot directly into existing 1103 sockets, a drop-in replacement that removed the last friction, keeping cautious customers on the fence. As yields kept improving through the early 1970s, the price kept falling, from around $60 per chip at launch down to roughly $4 each within a few years. What had once been an exotic, unreliable, barely manufacturable gamble was now simply the obvious, affordable choice. Inside Intel, the shift in mood was almost as dramatic as the shift in yield. Engineers who had spent the better part of a year bracing for the company to run out of runway were suddenly fielding purchase orders faster than the line could fill them. On October 19, 1971, barely a year after those first catastrophic test results, Intel went public. A A company that had spent its short life losing money on two unremarkable products now had a chip the entire computing industry wanted, and Wall Street noticed. The gamble that had nearly broken the company was now the reason investors wanted in. And as the 1103 spread through computer after computer, it was quietly doing something much bigger than winning a sales chart. It was making magnetic core memory obsolete. For roughly 2 decades, magnetic core memory had been the unquestioned standard for computer storage, reliable, well understood, deeply embedded in how the entire industry built machines. It had survived because nothing else could match its reliability at a price anyone could stomach. The 1103 broke that logic completely. It was smaller. It could be manufactured with the same photolithography techniques, driving down costs across the rest of the semiconductor industry, rather than requiring rows of workers physically threading wire through magnetic rings by hand. And critically, its price kept falling year after year in a way core memory's manufacturing process simply couldn't match, because core memory's costs were tied to human labor and physical materials, while silicon memory's costs were tied to a manufacturing process that was improving on almost a yearly basis. By 1973, industry observers were already writing that the trend was irreversible. Core memory wasn't going to catch up. It was going to be phased out, computer generation by computer generation, until an entire technology that had defined computing since the early 1950s simply stopped being made. The 1103 didn't just win a product category. It ended one. None of that would have happened if the chip had stayed the way it was in that Mountain View lab in early 1970, unreliable, expensive to make, forgetting data under conditions nobody could fully predict. The difference between a footnote and a foundation was those months of grinding, obsessive process work. The mask revisions, the statistical tracking, Grove's refusal to accept that the yield problem was simply the cost of doing business. It's worth pausing on why Andy Grove, specifically, was the person who pushed the 1103 through its darkest stretch, because his own history explains a great deal about the intensity he brought to it. Grove had not had an easy path to that fab in Mountain View. Born András István Grof in Budapest, he survived both the Nazi occupation of Hungary as a child and, a decade later, the brutal Soviet crackdown on the 1956 Hungarian uprising, escaping the country and arriving in the United States at 20 years old with almost nothing to his name. He rebuilt himself from there, learning English, earning a doctorate in chemical engineering from Berkeley, working under Gordon Moore at Fairchild, before following him to Intel as the company's third employee. That background left him with almost no tolerance for excuses and an instinct to treat every problem as something you could, and must, outwork. Colleagues who lived through the 1103 crisis with him later described a culture Grove was actively building around himself at the time, one where people were expected to argue ferociously about technical problems, sometimes brutally, while still remaining functional colleagues the next morning. He called it constructive confrontation, and the 1103's development is often cited as one of the earliest places that management style was forged under real pressure, not in a seminar room, but in a building with a roof that was cracking under the weight of the very equipment trying to save the company. Grove would go on to become one of the most famous chief executives in American business history, eventually writing a management book built almost entirely around the lesson that paranoia, a refusal to assume today's success guarantees tomorrow's, was what kept a company alive. It is not hard to see where that lesson was first learned. It was learned in 1970, watching a memory chip fail test after test, while a company with almost no cushion left waited to find out if it would survive its own most important product. He never described the 1103's development as some kind of triumphant war story. Decades later, he would still talk about it in almost clinical terms. The chip demanded, in his words, an unusual amount of orchestrated brilliance just to work at all, and even after it shipped, it carried flaws that meant that under certain adverse conditions, the thing simply couldn't remember what it had been told to remember. That's a striking thing for a company to ship anyway, and an even more striking thing for its own engineers to admit publicly, years later, without flinching. But that was the environment Grove had built and been built by. Fix what you can measure, ship what works well enough to be useful, and never, ever assume the current version is the last version you'll need to build. There's one more twist worth knowing, because it says something about how thoroughly the 1103 shaped the company that built it. For most of the 1970s, Intel's identity and its revenue were built almost entirely on memory chips, the 1103 and its successors. Grove himself would later say plainly that in those years, memory was essentially everything the company was. But by the mid-1980s, Japanese semiconductor manufacturers, Fujitsu, Toshiba, NEC, Hitachi, had entered the DRAM market with aggressive pricing and manufacturing quality that Intel could no longer match. In 1985, facing a business it no longer had a competitive edge in, Intel made the wrenching decision to walk away from the very market the 1103 had created for it, exiting DRAM manufacturing entirely to focus, instead, on a product line that had originally started as a side project for a Japanese calculator company back in 1971, the microprocessor. That side project became the 4004, and the discipline the company had built clawing the 1103 back from disaster, the obsessive process control, the refusal to accept good enough, the culture of relentlessly measuring what others simply assumed, is exactly what let Intel walk away from the business that made it and rebuild itself twice around something new. The company that would define the microprocessor era for the next 30 years was, in a very real sense, forged in the same overloaded, leaking, furnace-popping building where a memory chip almost didn't survive its own birth. Every dynamic memory chip built since 1970, every stick of RAM in every laptop, every gigabyte of working memory in every phone, every server humming in every data center on Earth right now, is a direct descendant of the same basic idea Bill Rijitz sketched out at Honeywell and Intel's engineers nearly failed to manufacture. The 3-transistor cell that made the 1103 has long since been simplified and shrunk down to a single transistor and a capacitor, packed together by the billions on chips smaller than a fingernail. But the underlying principle, data as a tiny electrical charge, constantly refreshed before it fades, traded off against speed and cost in exactly the way core memory never could be, traces directly back to that 1000-bit chip that spent its first year of existence forgetting things at random, blowing through 5 separate manufacturing revisions, and coming within one bad partnership decision of taking its own company down with it. The chip that was supposed to be a disaster ended up rewriting the rules for how every computer on the planet remembers anything at all. And it did it not because someone had a flash of genius that solved everything at once, but because a handful of engineers in a cracked, flooding, overheating building in Mountain View refused to stop measuring, refused to stop revising, and refused to let a 9 out of 10 failure rate be the end of the story.